The universe is 13.8 billion years old. That number feels solid, calm, settled. But hidden in a few pixels of infrared light, there's an object that seems to say, no, that timeline is wrong. Because according to what those pixels imply, something impossibly large was already shining when the cosmos was still learning how to turn on its first lights, when there hadn't been enough time to build anything that mature. Not a galaxy, not a monster black hole, not whatever this is. At first, the team thought it was a mistake, a processing artifact, a cosmic mirage. But then the data came back again, and the object didn't disappear. It got stranger. Tonight, you're going to follow the trail from a brand new space telescope's first surveys to a single, impossible object, that cosmic dawn that scientists can't explain. And near the end, there's an even bigger secret. Because this object may not be the only one. It may be the first warning sign that something about the early universe is missing from our story. So what exactly did James Webb just reveal out there, so far back in time it shouldn't be possible? Let's begin with the part nobody tells you. When the James Webb Space Telescope launched, it wasn't just a new camera. It was a time machine with a target list. Webb was built for one obsession, to look so deep into space that it would see the first galaxies, the first black holes, the first moments the universe stopped being dark. And that's not poetic language. That's physics. Light takes time to travel. When Webb looks at a galaxy 13 billion light years away, it's not seeing where that galaxy is now. It's seeing what it was when the light left, when Earth didn't exist, when the sun wasn't even a plan. That's why this story matters. Because if Webb is right, if this object is real, then the early universe wasn't just forming faster than we thought. It was doing something we don't understand. And here's the open loop you're going to carry for the next 25 minutes. How do you create something massive, bright, and structured when the universe has barely had time to create anything at all? The public version of Webb's story is all glossy images and triumphant music. The real story is quieter. It's people staring at data at 2 a.m., terrified of being fooled by noise. It's scientists arguing with each other because the universe doesn't care what your model predicted. And it's one moment, one red, stubborn smudge that refuses to fit. But before we can meet that smudge, you need to understand cosmic dawn the way Webb sees it. In the beginning, after the Big Bang, the universe was hot and bright. Plasma, particles, chaos. Then it expanded and cooled until protons and electrons could finally settle down into neutral hydrogen. And when that happened, the lights went out. Not literally dark in some absolute sense, but the universe entered an era where there were no stars, no galaxies, just vast hydrogen fog. Astronomers call it the cosmic dark ages. Then, slowly, gravity began doing what gravity does. Tiny ripples in density, barely different from place to place, started pulling matter together. Little clumps became bigger clumps, gas fell inward, pressure rose, temperatures climbed, and finally the first stars ignited. That was the first sunrise the universe ever had. The problem is, the universe doesn't do anything instantly. Even with gravity, even with time, structure takes patience. To build a big galaxy, you need generations of stars. You need mergers. You need the slow assembly of mass. So scientists made predictions, reasonable ones. At around 200 to 400 million years after the Big Bang, cosmic dawn, you'd expect small, chaotic proto-galaxies. Sparse, primitive, not much metal, not much dust, not much time. Now keep that expectation in your mind, because Webb was about to smash it. What happened next starts, surprisingly, not with a discovery, but with anxiety. Webb's first deep surveys weren't aimed at one famous target. They were wide, systematic sweeps. Programs like Sears and JADES, built to collect thousands of distant galaxies and let statistics tell the story. The teams were excited, yes, but they were also cautious. Because deep field astronomy has a history of getting carried away. You see a faint dot, you estimate a distance, you publish. And later, better data moves it closer, makes it smaller, makes it normal. And the biggest trap is something called a photometric redshift. Here's the simple version. As the universe expands, it stretches light. A galaxy's emitted light gets shifted toward the red. Longer wavelengths. The farther away it is, the more it's stretched. If you don't have a spectrum, if you don't have that clean fingerprint of wavelengths, you can still estimate distance by using filters. You take images through different bands, see where the object drops out, and infer how redshifted it is. It's powerful. It's how many early universe candidates are found. But it can be fooled. Dust can mimic redness. Certain emission lines can fake a dropout. A closer galaxy can masquerade as a farther one if the colors line up just wrong. So the rule is, photometric candidates are suspects, not convictions. And that's exactly why, when the first wave of Webb data arrived, the teams did something that sounds unromantic, but is everything. They checked, they recalibrated, they questioned their own eyes. Then, buried among the normal-looking distant galaxies, they saw one object whose colors looked outrageous. It was too red in exactly the wrong way. It didn't just suggest a high redshift, it screamed it. And the moment someone said, "This could be at cosmic dawn," another voice immediately replied, "Or this could be fake." So they ran it again. Different pipelines, different assumptions, different background models, different photometry apertures. The object stayed. And now came the first twist. If the preliminary distance estimate was even close to correct, this object wasn't just early. It was unbelievably early. So early that in the universe's timeline, it was appearing at a time when the first galaxies were supposed to be small and messy, but this one looked bright, compact, mature in a way nobody wanted to say out loud, because saying it out loud meant inviting a question that feels almost illegal in cosmology. How did it get so big, so fast? But that wasn't the biggest surprise, because when the team began translating brightness into physical mass, the numbers started to look dangerous. Astronomers don't weigh a galaxy directly. They infer mass from starlight, from models of stellar populations, from how much light you'd expect from stars of a certain age and composition. Those models are not perfect, but they're grounded. And yet this object, this stubborn smudge, was implying either an enormous mass in stars or an energy source far more intense than normal starlight. In other words, two possibilities. Yes, either the early universe made massive galaxies much faster than we think, or something inside this object is amplifying its light. And that raises a new mystery. If it's not just stars, what is it? At this point, but then this one didn't cooperate, because follow-up observations, deeper imaging, different filters, comparisons with other fields, kept reinforcing that it was unusual in a way that was hard to wash away with one simple correction. And that's when the second twist arrived. Scientists weren't expecting the early universe to be filled with objects that looked like this, but Webb kept finding more. Not identical copies, but cousins. Compact, extremely red sources at high redshift, some with properties that didn't fit standard templates. Astronomers started giving them nicknames, because when you don't fully understand a class of objects, you name them so you can talk about them without pretending the mystery is solved. And the nicknames were telling. Little red dots. Small, red, intense, far away. And now the stakes were rising, because one weird object can be a fluke, an oddball, a lensing accident, a measurement error. But a population is a message. So what kind of message could the early universe be sending? Here's where the science gets thrilling and unsettling. At cosmic dawn, there are only so many ways to make something extremely bright. One is to form a lot of stars in a short time, a starburst. That can happen when gas collapses rapidly or when galaxies merge and shock compress their gas. But even starbursts have limits. You need gas, you need cooling, you need time. Another is an active galactic nucleus, a supermassive black hole feeding on surrounding matter. When matter spirals in, it heats up and glows, and it can outshine an entire galaxy. That would solve the brightness problem. But it creates a new one. Supermassive black holes are not supposed to exist that early in such large numbers. To make a black hole huge, you either start with a heavy seed, or you feed it fast, possibly faster than typical accretion physics likes to allow. So if this impossible object is powered by a black hole, the universe still has a timing problem. How do you build a monster that early? And if it's not a black hole, if it's stars, then you have another timing problem. How do you build that many stars that early? Either way, the universe is cornering us into an uncomfortable question. What if the early universe was more efficient at building structure than our simulations predict? Or worse, what if we're missing a key ingredient? But then something else happened, something that doesn't show up in the pretty pictures. The debate moved from images to spectra, because there is one method that can turn a suspect into a confirmed distance, spectroscopy. Instead of just measuring brightness through broad filters, you split the light into a rainbow and look for specific lines. Hydrogen, oxygen, carbon, and other fingerprints. Those lines shift with redshift. If you can identify them, you can pin the galaxy's distance. Spectroscopy is hard at extreme distances because the light is faint and the universe is noisy. But Webb was built for this. So the teams pushed. They scheduled time. They aimed Webb's instruments. They waited. And this is where the story becomes emotional, because imagine what it's like to be on that team. You found an object that might rewrite an era of cosmology, but if you're wrong, you will be corrected publicly, permanently, and quickly. The only way forward is to let the universe answer in its own language, spectral lines. And when those first spectra started coming in across various cosmic dawn candidates, scientists expected clarity. What they got was a new kind of confusion, because in several cases, the spectral fingerprints didn't look like the simple, clean patterns you'd expect from a young, primitive galaxy. Some spectra hinted at strong emission lines, some suggested dust, some suggested energetic processes, and some were just difficult, ambiguous enough to fuel arguments for months. And that's the third twist. Webb wasn't just finding early galaxies, it was finding early complexity. Now, at this point, it's tempting to jump to the wildest conclusion that cosmology is broken, that the Big Bang timeline is wrong, that everything needs rewriting. But that would be dishonest. Science doesn't work that way. When an observation conflicts with expectation, the first job is to ask, could there be a simpler explanation? So scientists did what they always do when reality misbehaves. They attacked their own result. First, they asked, could the object be closer than it looks? Could dust in a nearer galaxy make it appear red enough to mimic a very high redshift? Dust absorbs blue light and lets redder infrared light through. A dusty star-forming galaxy can look deceptively red. Or could extreme emission lines from certain elements brighten particular filters and fake the signature of a high redshift dropout? Both are known tricks. Both have fooled astronomers before. Teams tested alternative fits. They ran different templates. They modeled dust. They examined whether the object's colors could match a lower redshift interloper. And sometimes the answer was yes for some candidates, which is exactly why you may have heard headlines that an earliest galaxy was later moved closer. But here's the open loop that matters. Even after corrections, even after reclassifications, there remained objects whose properties still looked extreme. Maybe not ZAO or 617 extreme, but still, why is it so massive and compact so early extreme? So even the conservative version of the story stays strange. And then, what happened next made the mystery more personal, because it wasn't just the numbers, it was the shape. In Webb's deep images, some of these early candidates appear compact, almost too tidy. In the local universe, big galaxies often have extended structures. They've had time to merge and spread out. They have disks, bulges, halos. So when you see something that looks condensed, bright in a tight region, you're forced to ask another question. Are we seeing a galaxy? Or are we seeing a brilliant core powered by something else? And that something else brings us back to the most dangerous possibility, a feeding black hole. Because if Webb is catching active black holes at cosmic dawn, then we're staring at the moment when the universe's first monsters were born, and their existence is not a detail. It's a crisis for our formation models. Here's why. To get a supermassive black hole, you need growth. The simplest path is to start with a small black hole, maybe from the collapse of a massive star, and let it accrete matter. But accretion has a speed limit set by radiation pressure. If you feed too fast, the emitted radiation can push infalling matter away. So to make a black hole 1 billion solar masses within a few 100 million years is like trying to build a skyscraper in a weekend while obeying every safety rule. Some theories propose heavier seeds, direct collapse black holes formed from huge gas clouds that collapse without fragmenting into stars first. Others propose bursts of super Eddington accretion, where the black hole feeds faster than the usual limit for periods of time. Others propose dense star clusters that quickly merge remnants into larger black holes. But here's the catch. Those are not settled pathways. They're plausible, they're debated, and Webb, by finding these extreme objects, is forcing that debate out of theory papers and into the sky. But this still wasn't the biggest surprise, because the impossible object wasn't just challenging black hole growth, it was challenging the timeline of galaxy assembly itself. If the object's light is dominated by stars, then it implies there were already large stellar populations very early. That would mean star formation started earlier, proceeded faster, or was more efficient than expected. And if that's true, it affects something enormous. Reionization. Remember the hydrogen fog? The early universe's neutral hydrogen absorbed ultraviolet light. For the universe to become transparent, that hydrogen had to be reionized, stripped of its electrons, by energetic radiation from early stars and galaxies. The timing of reionization is one of the biggest epoch markers we have. If galaxies were building faster and brighter earlier, they could reionize the universe sooner or differently than we think. So now the stakes are no longer one object. Now the stakes are the history of the universe becoming visible. And then, a new twist arrived from a direction few viewers expect: statistics. Because astronomers weren't just finding one impossible object. They were counting how many there were. And early analyses suggested that Webb was seeing more bright, massive candidates at high redshift than some models predicted. Not just one outlier, a density, a hint that the early universe might have had a more abundant population of luminous sources. Even if some would later be revised downward, the pattern was enough to trigger the most serious kind of scientific discomfort. The models were not matching the sky. Now, to be clear, cosmological simulations are complicated. They include dark matter, gas physics, star formation prescriptions, feedback from supernova, black hole growth, radiation fields. Small changes in assumptions can move predictions. So scientists started tuning, rerunning, and comparing. But every tuning raises a question. Are we improving the model, or are we patching it to fit an unexpected result? And this is where the documentary becomes human again. Because somewhere inside these teams are people who built their careers on a certain story of early structure formation. They didn't believe it in the casual sense. They tested it, published it, argued it, corrected it. And now Webb is putting pressure on the narrative, like a deep-sea submersible descending into a place where the hull starts to creak. So what do you do when the universe hands you an object that seems to exist before it should? You do the hardest thing in science. You slow down. You demand better data. You question every assumption. And you keep asking, what would have to be true for this to be real? One possibility is gravitational lensing. Mass bends space-time. A massive galaxy cluster between us and a distant object can magnify the background light, making a faint object appear brighter and bigger than it really is. Lensing can create false monsters. So teams looked around the object. Was there a foreground lens? A cluster? A massive galaxy that could be bending space? Sometimes lensing is obvious with arcs and multiple images. Other times it's subtle, caused by smaller structures and harder to model mass. If lensing is boosting the light, then the object could be less massive than it appears. That would relieve some tension, but it would create another mystery. If lensing is involved, what is the mass distribution doing? And are we miscounting luminous galaxies because magnification bias is distorting the census? One question answered, another one opened. And then, however, even lensing can't explain everything. Because some of these objects don't just look bright. They look compact in a way that suggests their light is coming from a small region, like a central engine. That brings us back to black holes again, because the universe is annoyingly consistent at leading us there. If a black hole is feeding, it can heat the surrounding dust, producing strong infrared emission. It can also produce distinctive spectral line widths, broad lines caused by fast-moving gas close to the black hole. So the next move is clear. Get better spectra, look for AGN signatures, measure line widths, search for ionization patterns. And this is where the tension turns into a countdown. Because Webb time is precious. Teams compete for observation slots. Proposals are reviewed. Schedules are packed. And the universe doesn't wait politely while we argue. Every year that passes, new data can either confirm the impossible or make it disappear. So the pressure builds, not just scientifically, but emotionally. You can almost feel it in the way papers are written, cautious language wrapped around urgent curiosity. And then this changes everything. The impossible object begins to act like a mirror. Because even if that specific source eventually gets revised, reinterpreted, or explained, it has already forced scientists to confront a deeper possibility. We may have underestimated the early universe's capacity for rapid structure. Maybe gas cooled faster in the densest halos than our subgrid models predict. Maybe feedback from the first stars didn't blow gas away as efficiently, allowing sustained star formation. Maybe the initial mass function of early stars was different. More massive stars producing more light per unit mass, skewing our conversions from brightness to mass. Maybe dust formed earlier than expected, changing observed colors. Or maybe black hole seeds were heavier and more common. Each maybe is a door, and behind each door is a universe that looks familiar, but not identical to the one we've been simulating. Now let's return to the center of the story, the object itself. Picture it. A faint red source in an ocean of darkness, a signal that has traveled for more than 13 billion years. It left when the universe was young enough that galaxies were supposed to be just beginning to assemble, and yet it arrives in our detectors as something that looks too complete. That's why impossible object is not a claim of magic. It's a confession of tension. It means, by our current understanding, this shouldn't be easy to make. But then, a final twist begins to emerge, and it's the one that may matter more than the identity of any single source. The early universe might be crowded with surprises. Webb is still young. Its surveys are expanding. Its sensitivity is revealing classes of objects we didn't have the power to see before. Some will turn out to be ordinary once we understand them, but some won't. And the real question is no longer, is this one object impossible? The real question is, how many impossible objects does it take before we admit our picture of cosmic dawn is incomplete? Because the first time you find one, you call it an anomaly. The second time, you call it a coincidence. The third time, you start rewriting code. And the fourth time, you start rewriting history. So where does that leave us tonight? Not with closure, with a horizon. In the coming years, Webb will keep taking spectra. It will keep pushing deeper. It will follow up candidates with better confirmation. Other observatories will join the chase. Roman will widen the field. Rubin will map the variable sky and uncover lenses and transients. And ground-based giants will deliver spectra with new precision. The impossible object will either be explained, or it will become the first page of a new chapter. And here's the emotional truth of this story. Every scientific era has its moment when nature stops politely matching the textbook, a moment when the universe reminds us we are not reading a finished script. We are watching it being written line by line by photons that have been traveling since before the Earth existed. Somewhere out there at cosmic dawn, that object is not thinking about our debates. It's simply existing. It existed when the universe was young. It existed long enough for its light to cross expanding space, and it exists now in our data as a challenge. A whisper from the edge of time saying, "You don't know me yet." So the next time you see a headline that says, "Scientists can't explain what Webb found," don't hear it as weakness. Hear it as the exact moment discovery is alive. Because the most terrifying possibility isn't that Webb found an impossible object. It's that the universe has been full of them all along. And we've only just built the first instrument capable of noticing. And if that's true, if this is only the beginning, then cosmic dawn isn't just the story of the first galaxies. It's the story of how quickly the universe learned to surprise us. And we are, right now, watching the first hints of that surprise come into focus.